So thanks everybody. We are here to talk about a bunch of scary low-level stuff that nobody knows about, right? So we're going to give a summary of attacks against BIOS and secure boot. The group of us here are from Intel Security. The rest of my friends here are from a group called Advanced Threat Research. And it's their job to find new attacks and find mitigations so that we can deploy stuff and make things better overall across all sorts of platforms, right? I'm actually from the Product Security Incident Response team. We coordinate a lot of these issues. We've been working with our friends at MITRE, actually presented yesterday and gave an awesome talk. We've been coordinating a lot of this stuff, and you know, we'd love to hear about more, even though we'd like to believe that there isn't more, but there's always something. And we'd love to hear from you at secure@intel.com, right? So we're talking about BIOS, right? And so BIOS, in the beginning, there was what we now call legacy BIOS. And it involved a lot of text, textual menus, and according to this slide, a lot of blue. Comes in various shapes and sizes, but mostly just blue. And it had to do all of these things. The system powers on and it has to go and put some instructions in the SPI flash that just to start getting the system ready. We're going to start running out of cache. We're going to start configuring memory, start running out of memory. We're going to start configuring a bunch of devices and get everything ready to go, run a bunch of option ROMs, and eventually we're going to find some kind of hard drive or boot media, and we're going to go ahead and find the master boot record and load it, and then that thing will start up an operating system, we think. And then along came the unified extensible firmware interface, and we got icons. And it's really interesting because now we also got a new color, black. And I mean, it did all sorts of good things, but really it's more about creating a standardized set of what I would call APIs, right? Things that you can rely on having happened by the time you run. And here's this slide, right? And everyone who has presented on security regarding UEFI has put this slide in their presentation. So here it is. We are doing that too because it's obligatory, right? And what it's really talking about is there's different phases. It breaks up the whole boot process into these different phases. And what's really going on is you're building upon the phase before you. It does all the same stuff that I was talking about. You start off running out of cache, and then you go ahead and set up memory, and then you go ahead and configure all of these devices, and eventually you come to the point where you're going to make a decision about what you're going to boot off of. You go ahead and make that decision. You load up a binary, and then, you know, that thing is a bootloader. It loads up an operating system, right? So one of the things that UEFI does is it gives you, well, two things. It gives you, it tries to get up to 32-bit virtual very quickly, and it just starts to run things, just like, you know, a regular loading of an executable. And then it also gives you these runtime services, which are standardized APIs that you can call even after the BIOS has finished its job and you're running at runtime. So with this came a standard for secure boot, right? And the way this sort of works is that, let's see, try and see my slide here. It's basically checking signatures, right? We start with assigned BIOS because if you could put whatever you wanted in the SPI flash, I don't know how many of you guys heard MITRE's talk yesterday, but they said it very nicely, right? Gee, what attacks can I come up with that I could do if I controlled whatever was in the SPI flash, which is the first thing that gets executed when the machine powers on. That would be any attack you can think of. So it's pretty nice. It's pretty nice if you can get there. So we have to start with this ability to ensure that what's there is right, and that's where the signed BIOS update comes from. And after that, you start checking signatures on everything that runs after you, right? So We get to these stages where we're running a dispatcher and we'll check a signature before we run it. We get to the bootloader and we'll check a signature before we run it. And that allows you to create an operating system secure boot that can then check the signature on all of the drivers before it runs those. And we'll be talking about attacks against all of that. So let's start. So the way that we're going to go about this is we're just going to go around this wheel. We're basically going to talk about different facets of attack surface on the platform firmware. And we're going to start with the SPY flash. You know, like I was saying, it's a pretty nice place. And so what we do on the platform is just so the nature of this, first of all, step back. There's a whole bunch of stuff here. We're going to blow through it really fast. That's why we mentioned we'll be in a hardware village afterward. If you really want to go into some detail and try and understand it with us, we'd be happy to walk you through it. So back to SPY flash. Like I said, it's a really good place to be. There's two real sort of methods to protecting it, right? One is based on system management mode. And system management mode is a different mode of the CPU, and it executes out of kind of a protected region of memory. And it's protected such that you can't read or write this memory while you're not in system management mode. All of a sudden you transition into system management mode, there it is. So one method is to use system management mode to protect it. You set a bunch of, you basically disable write access and then you lock it. And then if you try to re-enable it, it'll generate a system management interrupt. And that's what transitions the machine into system management mode, and it starts executing the SMI handler. So you have to set a bunch of bits in the BIOS control register, and that will lock the SPY flash from writes, and it will also it can also force writes to only occur when you're in system management mode. The alternate way, if you're not using SMM, would be to use the SPY protected ranges that are PR 0 through 4. There's 5 sort of ranges, and you can basically set up a base and a limit. That region gets protected, and you can set it to be write protect, and it'll be that way up until you reboot the platform. So there's two different methods. You know, you can sort of see what your platform does. You can go and find the BIOS control register, you can read it, and you can say, gee, what bits are set, right? So you could do that with some tool manually, and that's kind of a pain. So we wrote a tool called chipsec, and MITRE has a tool called Copernicus. Basically you can go and see what these bits are set to. So you can see at the top there you've got BIOS write enable, right? And you want to see that that's disabled, so 0. You've got BIOS lock enable, and you'd like to see that this is locked, and that's what will generate the SMI. And then you've got SMM BWP forcing that the writes have to occur when you're in SMM. So then we're checking the other mechanism as well, right? The red line down below is talking about what the SPY protected ranges are doing. So you've got the range itself in a write protect, and it'll be checking to see that you're covering the entire BIOS region. You can do either one of these things and it could work. So if you don't cover the entire BIOS region, then you're allowing somebody to write to that, right? And if they do that, then you get things like what Yuriy presented last year at Black Hat, where you can just sort of write whatever you want there, which could be shellcode, it could be just random junk that bricks the platform. It's bad. We're going to push all of our demos to the end because we've got a lot of stuff and we're afraid of running out of time. So we've got them. We'll get to them at the end. If you're really interested or if we miss stuff, come see us in Hardware Village and we'll have everything for you there. So here's a nice one. Teddy Reed presented something really cool recently where he was looking at a bunch of BIOS updates and seeing what they were doing, and in particular seeing who wasn't doing that. And this was really interesting, and he called it 1 days from hell, which is kind of a good word for it actually. In this update you can actually see the patch is adding the lock bits being set, right? But remember in the last slide I was actually saying there's a few lock bits that you have to set. There's actually a couple things you need to do, and it's not actually doing them all, so that's even more interesting. First mechanism was the system management mode, right? If you use system management mode, then you get a system management interrupt triggered when you try to flip the BIOS write, the write protection off, right? What if you could suppress SMIs? If you could suppress SMIs, then that system management interrupt would not occur. The system would simply have the SPI flash unlocked, and now you can write to the SPI flash. Well, MITRE presented a little bit earlier this year an attack where if the SMI lock bit is not set, then you can actually disable SMIs. And that does what I said. It kind of causes a problem. So basically you want to check your platform to see that this is set up and that it's locked. In particular, that it's locked. Remember the other mechanism. We can use the SPI flash itself with these protected ranges. Well, you have to configure those properly, right? So that's what we talked about earlier. But you know, you also have to lock that. So you can set it up and then not lock it, and then somebody could change it, right? So that's what the F lockdown bit is all about. And again, you can just check for that. So now let's talk about a different interface. We talked about SPI flash. Let's talk about BIOS update as an interface itself, right? So we were talking about all of these BIOS attacks, and we were thinking, oh, this is really complicated, low-level stuff that people don't know anything about, and so you'll never see it, right? Well, Mebromi is an example of this actually being done in malware, right? So they basically used a particular BIOS that did not enforce any sort of protection on its BIOS update interface. Simply used that BIOS update interface to introduce its little bootkit directly into the BIOS. Another issue, even if you have tried to protect the interface, is there is occasionally some data that you don't that you can't really trust. So in a few years ago, a talk by Invisible Things Lab showed an issue with an Intel BIOS where basically the image that gets displayed on your screen when you power up, yeah, that was just an image that was being parsed, and it was not really verified in any way. So they found an integer overflow that allowed them to take control right up in the early BIOS there just by substituting that image. Similarly, a little while ago, MITRE published an interesting thing with the update packets. So BIOS updates often break their packets, break up the update into a bunch of different little sections, right? Which then need to be put together when you're after you reboot and you're going to actually install the BIOS update. Well, what they found is that when they were putting this together, they were taking the fields of these packets and they were using that in a memcopy, and then they could basically use maliciously formed packets to take control right as you're doing the BIOS update itself. So then there's SMRAM. So I mentioned some of the protections are dealing with system management mode, right? So system management mode, I think I described it as having being a separate execution mode that's protected, right? Well, it's protected as long as it protects itself, right? So the first bit that we'll talk about is the sort of legacy or compatibility SMRAM, and I think this is best done with a picture. So normally you have code executing and you're writing to memory addresses, and you're usually writing to DRAM, but occasionally you find things like memory mapped I/O. With SMRAM, when you're in normal mode, normal execution modes, you will basically pass through and go straight to the system bus, right? When you're in when you set up SMRAM, you need it to be able to talk to actual DRAM, right? And that is flipped with these, with this particular register, some particular bits in this register. Basically, BIOS will set it up and say, it'll start out open and it'll load up SMI handlers there, and then you close it and lock it. And so you want to check that your BIOS actually closed and locked SMRAM. So after that attack, a few years later, so that was found like back in 2006, I think, by both Invisible Things Lab and Loic Duflot. You've got the same people a couple years later figuring out, gee, if I'm really just running out of RAM, well, the way the processor works is it just caches stuff. So if I can get the instructions that I want to execute in the cache for those addresses, then I can get it to run whatever I want, right? And that worked, right? So Intel introduced these system management range registers, which will force the non-cache area for those ranges, which would be SMRAM. So what you can do is just look at the platform and see, are those things configured? Is that set up properly? And I think I'm going to turn it over here so that the rest of this talk can be in Russian, because I think that would be really helpful to everyone, because it's really easy to understand this stuff.
Hey everyone, thanks for coming over. Even if you're here for dance talk. I don't know if this mic works or not, but so I didn't know this dude actually knows that much about BIOS. Yeah, so it was awesome. Okay, I'll continue. I'll continue describing attacks against SMRAM. It's important, and there are still questions. Why do you need to get into the SMRAM? Why do you need to compromise SMI handlers? If you have OS kernel privileges, for example, you can do pretty much everything. Well, there are a couple of reasons to do that. For example, according to government, you can get more implants. According to our friends from MITRE team, you can get bitten by a tick or a flea. I mean, just imagine, just think about that. None of the other exploits can get you fleas. So there are, on a more serious note, SMRAM, first, you got a code there, and it's pretty much protected, so you cannot really get it out of there. Plus, it can patch the OS, it can patch the hypervisor. More importantly, it can refresh the BIOS, so it can get persistency, as we showed a couple of some time ago. If you got that early compromise the BIOS, you can bypass or you can mount the evil mate attack, even against the full disk encryption systems that do use TPM, or you can bypass secure boot. So, continuing in the line of the attacks, one of the attacks that have been demonstrated using this chipset remapping capability. So, without going into gory details, basically, on the platform you have low MMIO, which can be like gigabyte, and if you have 8 gigabytes of memory, you don't want to waste 1 gigabyte of memory to the MMIO. So, there's a mechanism that is called reclaim. It intends to reclaim that memory, and so the way it works, there's a window that if you access that window, it's typically above 4 gig, it'll get remapped by chipset to the place, to the DRAM behind that, or lost to that MMIO. So unfortunately, I mean, it has to be locked, because if it's not locked, then the malware can use that. And the way exploit works is that the attacker can drop this boundary between DRAM and MMIO below SMRAM, and then use that remapping mechanism to remap to the SMRAM, right? So now your SMRAM is in the memory covered by MMIO. So obviously, the mitigation to that, and just use the lockdown configuration. Don't allow OS malware to reconfigure it. Oh, yep. That's actually a good, nice slide with a nice picture of how that actually works. This is a normal memory map, and this is how that works the attack. You drop TOLID, you access the memory reclaim range above 4 gigabytes, and chipset remaps it to above TOLID, which is now SMRAM. So you modify SMI handler, you inject a rootkit or a keylogger or something like that, and then you return back to that configuration. So your SMRAM now has malicious code. And there's a check for that. So I'll be flying through those type of slides. So the other type of attack, and I'll show you a picture. So normal system looks like that, including graphics, some graphic stuff. So for example, there's an MMIO bar that points to a graphics translation tables, and so they're used to translate access coming to this graphics aperture, which is a second yellow box, and translate access to that graphics aperture to graphics memory for graphics driver. However, that can be used to attack SMRAM as well. If assuming that the configuration is not locked, as in the previous remapping attack. So, for example, the BIOS forgot to lock the tollet. So how that could be used to attack? Somebody drops the tollet, similar to the previous attack, but instead of using remapping, the exploit could now. You can see that SMRAM now is an MMIO, so when SMI event occurs, CPU tries to fetch something, but not from DRAM, but from MMIO, but there's nothing there. So the attacker overlaps the graphics aperture on top of that. So there's a double redirection, and the chipset redirects through the graphics aperture according to the GTT entries that have also been replaced by the attacker somewhere else. That's the third redirection. So I kind of call it like in the tradition of Jean-Claude Van Damme, I call it triple redirection attack. So this way, using this multiple hops, the attacker can force CPU to fetch the code from some other place outside of the protected range. So the solution is same as in the previous attack. It's just make sure that the attacker cannot do those tricks, cannot reprogram configuration. You've heard there was a lot of research on DMA attacks, and obviously, if somebody can use DMA, let's say from a graphics card or from a network card, if firmware on those cards is compromised, or even from the OS kernel exploit that directly asks some of the cards to do the DMA to do the DMA to protected memory, you want to be able to protect system management mode code from those kind of attacks. And the way it's done in the platforms is there is a protection on the chipset level that basically says that if there is an upstream transaction, memory transaction, targeting SMRAM memory, which is defined as above TSEC base, then in that case, just block that, don't allow that. However, it still relies on the platforms and the BIOS firmware to actually lock down the configuration. So, for example, as in the previous attacks, if the BIOS forgets to lock down configuration and it allows malware to modify it, the malware could change the base of where the SMRAM is from chipset perspective. And therefore, once you do that, the DMA attack can work. So the DMA cycles are below TSEC, and now they are allowed to go through to the memory, right? There are two actually variants of this attack here. One variant is regular DMA from some add-on card, for example, network card at the bottom of the slide, and there's also another variant through the graphics aperture, which is treated as a DMA as well. So yeah, and we in a couple of weeks we're releasing a test for this vulnerability in the open source chipsec, so you can take a look at that. Other than protecting SMRAM, obviously there may be other issues, issues with the hardware configuration that it can be improperly configured. It can be reconfigurable by the malware, and that could result in certain attacks against BIOS, secure boot, and so on. So one of those attacks was demonstrated in 2007 at POC conference by person from McAfee. So the attack was a BIOS top boot block swap attack. So there's a mechanism in chipset that allows you to do a fault-tolerant update of the boot block. The boot block is the topmost block of the SPI flash, where the BIOS is, where the reset vector is, and so on. So normally, CPU, after coming out of reset, it starts fetching instructions from the last cache line below 4 gig. So at FFFFF 0 address, that's the reset vector. However, in order to do a fault-tolerant update, there is a mechanism that allows you to switch where the reset vector is. Basically, which block this reset vector will be executed from. And to show that on a better picture, so the topmost picture is the original boot, and the bottom part of the slide is when this top swap mechanism is enabled. So you can see that any access which targets SPI flash or firmware hub, or basically any ROM where a BIOS firmware is, it got swapped. So the reset vector now is an alternate BIOS boot block on the backup boot block. So obviously, if BIOS allows to do those kind of tricks to the OS malware can enable top swap mode. And then because this has to survive reboot, the malware reboots the system, and the CPU will start fetch instructions from somewhere else. It could be all Fs, and that you'll get an unbootable system, or it could be malicious code if that piece, if that alternate boot block wasn't protected. There could be a malicious BIOS boot block. So the way to mitigate that is essentially block malware's capability to modify boot block. Okay, so now obviously people realize that attacking SMRAM through some hardware tricks or configuration tricks is not enough. There's a whole bunch of software running in the SMRAM. Those are called SMI handlers, and they've been developed a couple of decades ago. With nobody thinking about security back then. Well, not security of SMM, not overall. But so there may be bugs there, and one of the first types of attacks that have been discovered and published in 2008 or 9, I forgot. So basically, you have SMRAM, and you have a bunch of firmware running there. And I'm due for a shot. Sorry.
Take your time.
Yeah.
Y'all know why we're here. I just want to point out, I was walking out as we were walking up here to shot these guys. So there's this guy walking out, and I pegged him, and I said, "Why are you walking out of this talk? I thought this would be a pretty good one." He's like, "Hey man, it's over my head." It's like, so I'm a kernel programmer from way back. That guy's a pussy. So, all you got it going on. All right, how about some love for the new speakers? Wait, where's his shot?
He has it. Yeah. Already got it.
Yeah. Dude, do it again. Oh, sorry, never mind.
They were too late.
That was wrong. I'm sorry. As you were.
Okay, so where I was. Oh man, that memory plays tricks with me now. So types of vulnerabilities in the SMI handlers. The first type was discovered is that there's an SMI handlers, but a lot of the routines that they use, let's say talk to hardware, let's say talk to RTC, talk to power management registers, and so on, they're wrapped into functions. But there's a precious space. A SPI flash is a precious space, so you cannot really move that code to the SMRAM all the time. You already have that code in the BIOS, which is in the DRAM. So why not just use it and call it? And that's what SMI handlers did. I mean, they just, you can see call, F000, segment selector, called segment selector, with some EIP. Right, and it happens to be translated to a physical address in F segment below 1 megabyte, which is not protected. So, that's how it works. Somebody found this out and replaces that function that the SMI handler calls with the malicious code. And the SMI handler will do the job for you, so it will just invoke that function. So, yeah, that has been published, and interesting is that the vulnerability disclosure had disclosed just 14 issues in one SMI handler out of 30. So, which amounts for hundreds in one single BIOS. And remember that platforms typically use the same BIOS. So, in going to EFI, obviously this type of vulnerabilities went almost away, because the EFI BIOSes still want to invoke something from outside of SMRAM, and in that particular example, the EDK-based SMI handler, it wasn't directly calling the function. It was actually reading the function pointer from the ACPI non-volatile memory, which is not non-volatile, it's actually in DRAM. So, and then calling it. So pretty much same type of problems, but just slightly different. So now I am switching to the attacks against secure boot we've been researching that area for a year and a half, and I'm giving the microphone to Alex. He'll start with the attacks against secure boot.
My name is Alex. So I will describe a little bit about secure boot and how we attack secure boot. So basically, the most important things in secure boot implementation is hierarchy, key hierarchy, and there is platform key, which is vendor root key. This key need to verify key exchange key. And key exchange key need to verify whitelist and blacklist signature for modules and binary, which we can load if secure boot is enabled. So platform key is stored in non-volatile memory in SPI flash, and it's a UEFI variable which is protected. And BIOS check if BIOS can find the platform key, then they allow enable secure boot. If not, BIOS assume that secure boot is disabled. So based on this, we create our first exploit for secure boot bypass. For this exploit, you need to have vulnerability in write protect mechanism in BIOS. So basically, we will talk a little bit about this exploit. We just, as a regular UEFI variable, platform key has a name, GUID, and a body. So if you corrupt the name of this variable, then BIOS didn't find this variable and assume that BIOS was disabled, so we bypass secure boot. And as you can check in this slide, so in the left hand we have original dump of SPI flash platform key, and the right hand we have with our modification when we corrupt platform key. And there is a high-level picture of our attack. So we corrupt platform key for compromised BIOS, and after that we install bootkit to UEFI file partition and patch kernel for compromised full system. And there should be demo. This slide should be joke, but I skip it. When we start thinking about how we can bypass secure boot and how BIOS should implement secure boot internally, we were thinking about that there should be some non-volatile variable, secure boot enable, which should show that secure boot enable and disable, and BIOS behavior should be different related to this variable, and we checked it and we didn't find. So the next very good experiment which we did is create two dump full SPI flash, one of when secure boot enable and one of when secure boot disable, and compare this dump. So if you try, good luck with that. It's not really easy. But after that, we implement our forensic functionality in chipsec. So you can parse SPI image and extract all DLLs, all Dixie drivers, all UEFI variables, and compare it independently. And we cache very interesting UEFI variable, which is named setup variable. It's runtime variable, so you can modify it from ring 3 from Windows API. And if you flip that 2 bits, you can just very easy disable secure boot. So basically, just one very simple Windows API function, and flip 2 bits from ring 3, and you can disable secure boot. So there should be a second demo, and will be in the end of the talk, and Andrew will continue to talk about this.
Hi. The policies. Policies is a way for the BIOS vendor to configure the image verification behavior. So the BIOS vendor may choose to skip image verification if the image is loaded from supposedly protected SPI flash, or choose a different behavior when the image verification is failed, like ask a user or even allow the image execution, which is kind of weird. So this is how the policies are implemented in open source EDK2. So as you can see, they are fixed values that are taken from a platform configuration database, so they cannot be changed in runtime. But sometimes BIOS vendors may choose some flexibility and decide to put them in setup. So this is an actual screenshot from a secure boot image verification violation, and this gives us a key where to look for these values. And setup variable did have these values. After some trials and errors, we found the location. So here they are. As you can see, this 044 are for option ROM policy, fixed media policy, and remove media policy. 0 is allow execute, and 4 is for deny execution. So all we need to do is just modify this setup variable and set these values to 0, which is allow execution. So this way, the secure boot is still enabled, but no verification is performed. So you can load whatever you want. So, and this issue was discovered together with Mitra guys. This is a slide from their presentation. So, they did a reverse engineering, and this code shows that the actual values for the policy are taken from setup variable. It should be a demo. Just skip. Oops. So, a couple of guidelines to BIOS vendors how to avoid these issues. So, first of all, if you protect the settings, if you decide to put them into UEFI variables, make these variables boot time accessible and don't expose them to operating system and untrusted software. Make these variables authenticated, so only who knows the key exchange key can update them. And check if that the user is physically present when modifying the values. And of course, set the default and image verification policies to secure values. Like, don't use always execute, allow execute as default values. So, and image verification handler should take care not only on secure boot settings and policies, but it should only check if the executable image has a supported format. Currently, the only supported format for is a PCOF image. So the BIOS firmware can verify the signature and image only if it's PCOF. So does BIOS specification defines other executable formats? Yes. There are two other formats. The first one is EFI bytecode. It's actually the same PCOF image wrapping around the EFI bytecode. And there is a so-called terse executable T, which is not a PCOF image. But the only difference of this format from PCOF image is a T header. This header is much smaller than PCOF header, and this was done to conserve the precious space in SPI flash. So the T images are usually loaded from SPI flash. So, and let's take a look at the actual implementation inside a UEFI BIOS. So we did parse SPI flash dump with a chipsec, and we found the Dixie drivers that actually implement the image verification library. It's core dixie.uefi file. So loaded it into IDA Pro, and we found the function. To the left is a image verification handler. What it does, it calls a function that checks the executable image is a valid PCOF image, and it returns an error if it's not. And if it returns this error, the image verification handler routine just checks if the error bit is set. If it's not, it continues the execution. But if the error was returned, it just returns 0. which actually UEFI success. So no verification is performed. It's just skipped. So the secure boot is still enabled, but no verification is done. So that attack is simple. Just get the UEFI executable, a bootkit, convert it to TE format by replacing the PCOF header with the TE one, and replace the operating system loaders on the UEFI partition, and that's it.
All right, we have 5 minutes, and I want to show at least one demo because we have 4 or 5 demos there. You can catch us later. We can show more demos. So, but a couple more issues. I'll fly through the foils. So, other problems that we have discovered is some of the BIOSes, they enable CSM, which is a compatibility support module, which allows you to boot legacy OS on top of UEFI firmware. Basically, enabling CSM with secure boot. That's a bad idea, because secure boot should check signatures, but the legacy boot doesn't know about signatures at all. So the other problems are some of the systems allow to restore secure boot configuration and keys, or set them to restore to defaults, or clear them. So remember the first attack, corrupting PK? If you clear secure boot configuration, which will remove platform key, guess what will happen? Secure boot will get disabled. So some of the BIOSes, they actually store a bit that tells them to start this clearing in an unprotected configuration available to the Ring 3. And this was my favorite. This is not really an exploit because we didn't need to do anything. I mean, what we did is on some of the laptop on specific model of specific vendor, what we have figured is we could change the configuration of secure boot. We could disable it, but they've implemented a signature or hashing scheme where they actually store the hash of the critical configuration somewhere, and then they check if it's changed. Then they ask, hey, tell the user, hey, it's changed, you know, and so what they do is they beep 3 times, wait for 2 seconds. We didn't catch that attack immediately. We actually figured this out in a week or so. Then they continue booting with the changed settings. So, and this is the cryptic message that you should be able to, you know, do something urgently because somebody is trying to boot the bootkit on your system within 3 seconds or 2 seconds, I don't remember. So there are other problems with the BIOS, for specifically settings. For example, Jonathan Brassard disclosed a vulnerability some time ago that the BIOSes don't clear the keyboard buffers. So you type BIOS password, HDD password, or pre-boot authentication system password, and then it lies around in memory available to everyone. So the BIOSes need to clear that, and we actually have a test that you can use and see if your BIOS in your system clearing that. So. SMI handlers. Again, we have 1 minute, so I'll just say a couple words that we do continue research in vulnerabilities affecting BIOS and secure boot, and we do continue coordination with all platform manufacturers and BIOS vendor. Specifically, we're in the middle of coordinating multiple issues affecting UEFI-based SMI handlers. And the last words. So. One may think that all of these attacks, they require kernel mode privileges. And typically, yes, because you work with the hardware, you work with the BIOS, you need to talk to the interfaces, hardware interfaces, I/O ports, PCI config space, physical memory. So yes, technically this is a kernel privileges. However, what we've discovered co-discovered with MITRE team is that there are kernel mode drivers that actually do that for you. So you can ask to add to physical memory or I/O ports or MMIO or PCI config, and they would do, and they are assigned for all versions of the Windows that require signatures. So yes, that makes all of those attacks, even those that initially required kernel mode privileges, as user mode. So you can compromise BIOS, you can compromise SMM, you can bypass secure boot, you can enable evil maid attack from user mode. And there are guidelines. and there are lots of research. I do want to thank all of the researchers that work in that obscure area, because this is a baseline for the security of the entire platform. And you can catch us. I don't have a time even for one demo, but we will have videos available of all of the demos from this talk. Or you can catch it at us at Hardware Hacking Village. Thank you. Thanks everyone for coming. Do I have one more minute? No? We're done? Yes. Oh, so really sorry. So we have one more minute. So I'll attempt a live demo of actually, bypassing secure boot on the same system we've been presenting. You figure why we actually staged it to the end of the presentation. So.
Now you get it.
So anyway, so secure boot is enabled. I'm not showing that, although I usually do. So we launched the exploit, which is PET header exploit. What we did was we just replaced bootloader. That's it. But the bootloader with the bootkit, but the bootkit has a different header. That's it.